Alright guys, we're going to do a few more examples of limits today, and I want to point out a couple of things that people struggled with, and definitely was a piecewise function and also a compound fraction. So I want to do a couple more examples of those before I do the other things I want to do with you. Here's an example of a piecewise function, and we've got two different equations. We've got this polynomial, this rational equation, if x does not equal 2. This means everywhere else except for 2, we're going to be looking at this graph. And then we've got this single point. When x is 2, y is 6. Now let's go take a look at this picture. What does this look like? We've got this graph here, and we can see this is a piecewise function, and everywhere else we've got that rational function, but at the specific point 2, we're up here at 6. And we're interested in what is the limit as x approaches 2 of this graph. Well, looking at a piecewise function, you need to make sure, all you have to make sure for a limit is make sure that from the right and from the left we're approaching the same value. So we're looking at x is approaching 2. This is where we need to focus in our eyes. So from the right is this black arrow I have here. That means, from the right, where are we heading? And we're heading towards that y value of 4. And from the left is this other arrow. Where are we heading? We're also heading towards this y value of 4. We don't really care what happens exactly at 2. We just want to look around 2, close to 2, in that neighborhood. Do we have a graph that's matching up and heading towards the same y value? That's the intended height of the graph. That's where it's trying to get to. Even though at that point it jumped way up here, this answer is 4. Because that is the y value we're heading for. Even though that y value up there is 6, so we got to get that down. So when you have a piecewise function, you're going to need to graph it and take a look at it. Now, some piecewise functions, though, as we saw from last night's video, don't match up. They don't line up. We looked at the piecewise function last night, and it didn't line up. It had from the left it was -1, and from the right it was 1. Okay, so let's go on and see if we can't do another example here. Alright, I've got a piecewise function, y squared plus 5, if y is less than -2, and 1 minus 3y if y is greater than or equal to -2. And let's take a look at the limit as y approaches, say, 6. Now, if y is approaching 6, we are going to be looking at this bottom function because that's what we use for all y values that are bigger than or equal to -2. So we would just be looking at that one right there. And you can just plug in 6 for y and you're going to get 1 minus 18, which is -17. And that's no problem at all. But where this can get tricky is if I ask you the limit at at y approaches -2. And -2 is where these two graphs meet. And so we would need to know, whether or not these two graphs are trying to meet. Are they trying to head towards the same value? And an easy way to do that is find out the limit as y approaches -2 of both of them. Plug in -2 to both of these functions. So if we plug in -2 for y into the top one, we get -2 squared plus 5, which is 4 plus 5, which is 9. And if I plug in -2 into the bottom function, I get 1 plus 6, and I get 7. And you can see that these are not the same value. So as y approaches -2, the limit does not exist because we were not heading towards the same y value. Alright, this one people really struggled with today, so I want to give an example of this. This is a complex fraction, and these can be fixed or made to look better if you separate it out. And this is what I mean. Instead of doing divided by x, I'm going to do multiplied times the reciprocal. You know that thing we learned in 7th grade? Thank you, Kimmy. That thing we learned in 7th grade to multiply by the reciprocal? And then here, we're going to bring these two fractions together. And I've showed you guys this little shortcut. You can do 5 times 1 is 5. 5 plus x times 1 is 5 plus x. And we're subtracting those. And then you multiply the denominators together. That is a shortcut for bringing those two fractions together. Let's see that again. 5 times 1 is 5. 5 plus x times 1 is 5 plus x, and we're subtracting, so that goes right there. And then you multiply the denominators. And we're still multiplying this times 1 over x. So if we clean up the top, I get negative x over 5 times 5 plus x, and I'm multiplying this times 1 over x. And I cancel these x's, and I get negative 1 over 5 times 5 plus x. And we plug in 0 for x, and we get negative 1 over 25. So I wanted to give you another example of that. Okay, whenever you plug a number in and you automatically get 0 on the bottom, but you do not get 0 on the top, this is not indeterminate. This is definitely a does not exist limit, because you are dealing with a vertical asymptote here, I guarantee you. Anytime you get not 0 over 0, let me write that down, not 0 on top, but 0 on the bottom, you are dealing with the vertical asymptote, and the limit does not exist. You are either heading straight up or straight down. You either need mountain climbing stuff or you need scuba gear. You'll see more on that later. That probably didn't make too much sense, but well, oh well. Okay, the last example I want to do with you is a limit, and we're not looking at a specific graph, and it's in a different form, and I've got an h here instead of an x. We still are going to answer this like normal. We go ahead and plug in 0 for h, and do our math, and we get x squared minus x squared, and we get 0 over 0. Again, this is called indeterminate, which means that you could there it is. Had to work on my spelling there. Okay, that's not even right. Really? Let's try that again. Indeterminate. Yes. Whatever. Okay. So here, we're going to see if there's any algebra we could maybe do. For example, x plus h squared is x plus h times x plus h. And of course, we know that's not x squared plus h squared. None of us think that, right? Right? We're going to FOIL this, right? We're going to do this little happy face thing, right? We're not going to think that that's just x squared plus h squared. So we have to do that. And we get x squared plus 2xh plus h squared. And that's just this x plus h squared part. So I've got limit as h approaches 0 of x squared plus 2xh plus h squared. And then I still have the minus x squared, and this is all over h. So let's see if anything canceled. Let's see here. Oh, looky here. That cancels with that. So I have the limit as h approaches 0 of 2xh plus h squared all over h. Now at this point I can factor an h out of the top, and that's going to leave me 2x plus h over h. These h's cancel, and now when we plug in 0 for h, we don't get 0 over 0 anymore. We get another function, which is 2x. And I don't want to spoil the surprise, but I guess I'm going to. This is the derivative of x squared. So you just took a derivative, and this is how we do that in calculus. Well, it's one of the ways that we do it. It's the way we do it at the very beginning. So we didn't get an actual number at the end. We got a function instead. 2x is the derivative of x squared. And we're going to learn that that's a slope finder and how to find tangent lines and do all kinds of crazy stuff with that. So anyway, I will see you guys tomorrow.